Welcome to Calculus Chat, a weekly discussion with your lecturers for 114. I'm Dr. Biggs, and here with me is Dr. Kellerman
Hello.
and Professor van der Walt.
Hello.
Okay, so our second week is just about over. I think we are now quite solidly into the semester. We've got 2 worksheets done, and the first test is already behind us. I hope that went well enough for our students. Right, so shall we have a bit of a discussion about what's been happening? So in the TUTS, we've continued working on some of the foundational things, right? In worksheet 2, it was still based on the first week of lectures, where we looked at inequalities and a bit of sets and a revision of a bit of trig and so on. And of course, the absolute value. And I don't know about you, but in my tutorials, we had some very nice discussions on proving things. And some of those, especially those absolute value properties, can seem deceptively simple and feel like they should be very easy to prove, but to actually spell out in detail and make a good argument for a proof, well, it takes some skill and it takes some effort.
Yes, proving and writing mathematics in a clear and cogent way is a skill, and it's a skill that must be practiced. And it's again one of those things that you don't get better at by reading how other people did it necessarily. You have to do it yourself.
Yeah, you have to do it yourself. And often there are more ways of solving a problem. And I think one of the best experiences or the rewarding experiences we have as teachers are when students come with unexpected ways of solving the problem. And sometimes it's even better than the way that we had in mind.
I would also say mathematics is hard enough as it is. So don't make it any harder by giving difficult explanation. Make your explanation as clear as possible so that the reader can focus on the actual mathematics and not have to waste mental energy to try to decipher your argument. So when a student writes out a proof, explain your argument very clearly as though you're explaining it not to the lecturer but to a fellow student who wants to understand the work. Explain exactly what you're doing, motivate it, and don't hesitate to write grammatically complete sentences instead of just writing cryptic symbols as students often do.
No, certainly this is a thing, I think, a misconception many students have, that in mathematics, I even had one student one year become quite upset when I told him I want to see some sentences and some words in their answer, because they have this idea that, no, this is maths, they should only be symbols and maybe something special to connect those two. But that is not at all the way we do maths. The way we do maths is we are in effect telling a story and telling an argument to try and convince somebody. And doing that effectively involves lots of words. So just like when we explain a problem, we're using lots of words. You need to communicate what you are doing. Well, I think I'm going to start here. Then I'm going to break it up and I'm going to do this part first and then that part first. And then putting it all together, I find this. All of those words should be part of the story you tell, part of the argument you make.
Yeah, a clever idea is only as good as your ability to communicate it.
Absolutely.
I just think, like you said, there's more than one way to prove most things, almost everything. And once you've gotten a proof, go through the proof and see, well, can you simplify it? Are there unnecessary things in there? Make your proof as nice and elegant as you can. Right? It's good practice in constructing good mathematical arguments.
Yes, it reminds me of, I don't know if it's a quote or a joke that I saw somewhere that proving something in mathematics is like scaling a very difficult and hard cliff. And you're climbing up there and you're slipping and you're sliding and you're sweating and you're having a lot of trouble. And when you get to the top, you see there's a nice tar road all the way up.
Yes, it's exactly like that.
And that is very often the case, is you need to go through the trouble and the struggle of proving it in your own way to actually see the simpler and the easier way of getting to that answer.
Yes, I think that's a very nice analogy. I mean, once you get to the top, look down and enjoy the view and see if there isn't an easier road. Very nice. I like that.
Yes, if you have a plan B and a plan C, in one of the tutorial questions this week, I think it was solve the inequation cos squared x greater or equal to 1. We ended up having 3 different approaches. It's always a good idea in mathematics to have a plan B and even a plan C, and sometimes you end up finding an alternative solution that appears to give a different answer, which can be very useful because then you know somewhere you've made a mistake, one of your solutions is wrong. So if you can find alternative ways, always try and have a plan B and even a plan C if possible.
Absolutely. I mean, that's what I like doing myself when capable. Even if you think that you've got the answer right, try and do it another way and see, do you still get to the same answer? If you don't, haha, then there's a discovery to be made. Okay, so what was covered in lectures this week? Well, we started on functions, right? And functions are going to be the main object that we'll be playing with throughout the course. And I'm sure we're going to have some more fun next week in the worksheet when we start proving various things about functions, right? Because we've introduced some types of functions, well, functions that are injective or surjective, functions that are even or odd, functions that are increasing or decreasing. And then you can start asking interesting things like, is it true that every odd function is increasing? Or is every odd function increasing or decreasing?
Yeah, I think there's lots of fun questions to play around with. We're really now dealing with a fundamental object that we need to understand if we want to do calculus. I mean, you can't do calculus without functions.
Absolutely. And then next week in lectures, we're going to, I think, if functions are our fundamental object, we're going to introduce our fundamental tool, which is the limit, to play around with functions. And we're going to be expressing many concepts in terms of limits as we move throughout the course.
Yes, so this is a really nice topic, and like you say, it's the fundamental thing here. Everything in calculus we express in terms of some kind of limit, and it's a deep concept that has many children in mathematics. Lots of mathematics that grew out of this concept of a function, and which grew out of mathematicians trying to understand this concept of a limit better.
Yes, and so Professor van der Walt is going to be taking over those lectures for the next theme. And I've had a quick look at the first video already, and he's going to be taking you on a nice, beautiful tale of the history there. And it is quite a beautiful history with all kinds of things happening there. I mean, just the invention of the limit, as we've talked about before, was not a trivial thing. People were playing around with these ideas before they managed to bring in the limit and found that was the appropriate language to express this idea in very well.
Mm.
And the one part of the history that I like very much there is the controversy between Leibniz and Newton when it gets to the calculus.
Oh yeah, big fight broke out, about who was first, who got there first, and I think it was terrible for people on both sides. I mean, it wasn't a physical war, but I mean, I think it set back mathematics quite a bit because, on the one hand, you had the Newtonites, and on the other hand, you had the Leibniz guys, and, kind of didn't want to talk to each other. So I think that was really bad for mathematics.
Yeah, I mean, it was interesting. The Leibniz being more on the continental Europe and Newton being in England, in the UK, and they both wanting the honor for their country that they are the foundation. And it's actually interesting. You can still see that kind of a schism between those two traditions still lasting in some ways today. You can see the effects that it had, that the sort of the sharing of ideas and the interplay of ideas stopped for quite a while because of this divide.
Yeah.
So I believe Newton was also, he had an interesting personality. He was in a lifelong nasty academic confrontation with Hooke over certain discoveries, and he was very sensitive to criticism. He couldn't tolerate criticism of his work.
Now, he was apparently not a nice guy at all.
Yeah, he was not a nice man.
Well, that doesn't mean that he didn't do nice mathematics and nice physics. I mean,
no.
Yeah. Well, but both Newton and Leibniz were highly accomplished people outside of mathematics as well. I mean, Leibniz was actually trained as a lawyer, and he's also famous for his philosophy. And Newton was, what was it, Chancellor of the Royal Mint or something like that.
I know, it's actually very fascinating once you start reading about the personalities involved and their lives.
Mm.
Also, as a physicist, if you think about it, How clever was it that Newton figured out that it's the same force that causes things on Earth to fall to the ground as what causes planets to revolve around the sun?
Yeah, no, that's quite the leap.
Well, I think that demonstrates very well the absolute power of mathematics, because I think it's most likely that, he figured out that, well, look, the mathematics is the same. The same equations governing the apple falling governs the motion of the planets. Well, I'm speaking under correction, he may have had some other kind of insight, but I can just imagine, that mathematics would lead to this discovery. And to this day, it still does.
Yeah, I mean that's the power of trying to recognize patterns and finding the correct language to put it in an abstract way. And the abstractions for many things can have the same abstraction, and that's the power.
Yes, I'm always very impressed. His law of universal gravitation, I find it mind blowing how he came up with it.
Yeah, no, I mean he definitely made a huge impact on the world with his discoveries, and it's quite amazing.
But
Um,
could one say that Newton's approach to calculus was more inspired by physics and Leibniz's approach was more inspired by mathematics?
I think one could say that. If you think of the way they conceived of limit, so Newton used, they both used what we would call today infinitesimals, which means a quantity which is not zero but smaller than any other. But Newton's infinitesimals he called fluxions, which was a more kind of a dynamic thing. He thought of it as moving a very tiny little bit, whereas Leibniz's infinitesimals were more kind of static.
mhm.
So I think we're more related to kind of problems in geometry,
Uh-huh.
tangents and the like.
Yes, no, they certainly had quite different approaches, but amazingly were coming up with a very similar theory of calculus. And I mean, philosophically, it sounded like at the time there was some serious doubts about these infinitesimals and whether you could even talk about something which is infinitely small, whether this is a sound concept.
Yes, in the 20th century, I would be remiss as a model theorist if I didn't mention this. The model theorist Abraham Robinson developed what he called nonstandard analysis. So he took all these informal, hand-wavy notions about infinitesimals and he formalized it in a rigorous axiomatic framework. So basically, he treated infinitesimals as though they were actual numbers. So worked with the hyperreal numbers, which are an extension of the real numbers, where you have, if you like, infinitely small numbers and infinitely large numbers, and put it on a solid axiomatic footing and showed it can actually be rigorously developed.
Hmm.
So that it's not the approach that is classically followed. I think the usual approach is to work with epsilon delta definitions and those kinds of things, but it can actually be done rigorously if you do it correctly.
Yeah. So speaking of that, we are going to rely on this long history of beautiful mathematics and development and take, well, what is the common classic approach that's come from that. And that is the epsilon delta formalism that you will certainly be seeing in lectures. That is quite a formal way of putting it, but it captures the idea really beautifully and in a very concrete way. There's no doubt about what we mean when we say that the limit of something is that. We can all agree that it has that very specific meaning.
Yes, the definition of a limit, it's one of those things. It's quite a tricky definition for students to handle, and it's surprising how long it took from the time that Newton and Leibniz introduced or discovered calculus. And I mean, people immediately jumped on calculus as a very powerful tool in mathematics. It caused an absolute explosion in mathematical discovery, but it took 200 years or so for mathematicians to settle down and say, okay, well, wait, let's write down the proper definition, people. That only happened in the 1800s with Bolzano and Weierstrass and Cauchy as well.
Yeah, I think also this week we saw some examples of the triangle inequality where you prove a statement: if absolute value of a plus 3 is less than 2, then some other absolute value is less than 7, that kind of result. So that's not just an interesting application of the triangle inequality, that will actually come to play when students do epsilon delta definitions later on. So some students asked, must we be able to apply the triangle inequality? Can we not solve those kinds of questions just by solving the inequations? But please be able to use the triangle inequality, because you'll need it when you do formal definitions of limits and continuity and such. Sorry, Jan, I interrupted you.
No, not at all. I mean, you make a very good point. So in 114, we are going to discuss the formal delta epsilon definition of a limit, but we're not going to focus on that so much as on developing an intuitive understanding for how things work. And then we're going to have some what we call limit laws, some rules for manipulating limits. And using those in a rigorous way, we will be investigating limits. But this kind of application of the triangle inequality you mentioned is extremely important for dealing with limits in the delta epsilon form, which you will be seeing a lot of next semester and in your second year and in your third year. So it is important to get comfortable with that kind of argument.
Yes, it's certainly we need to develop that way of reasoning well. It's going to come up all over the show.
This if then.
Now, for students who are wondering, epsilons and deltas they usually denote very small numbers. And an interesting story, the famous mathematician Paul Erdős, he referred to young people as epsilons. Basically, children were epsilons. That was his phrase for referring to children.
Okay, well, there's one last thing that I wanted to discuss a little bit, and that is, well, as I mentioned already, is Professor van der Walt is going to be taking over lectures in the next theme, and he's going to be there for about 2 weeks to cover theme 2, and then after that, Dr. Kellerman is going to take over. So, I mean, that is the nature of how we are sorting out things for this online presentation, but I think there are some nice advantages, right? Each lecturer has maybe a different way of doing certain things. They have a little bit of a different style about how to approach certain problems. And it gives you exposure to different ways of thinking. And this can be an extremely valuable learning opportunity.
Yes, absolutely. I think it is essential for students to get exposed to different perspectives on the same thing, because there are different perspectives. We're all mathematicians here. And so we agree on the basic rules of mathematics. We agree that we're using the ZFC system of axioms, and we agree on using classical propositional calculus to perform our logical arguments. But when it comes to the interpretation of mathematical statements and say things like what is the best proof for a statement, or what is a nice way of understanding something, then we all have very different ideas. And it's a good idea for students to get exposed to these different ideas so that it helps them develop their own unique perspective on the material.
Yes, you get 3 lectures for the price of 1.
Woohoo!
What a bargain.
In fact, I see Professor vandenberg will be including some of his lectures.
Yes, indeed. We will later on in the semester. We will make use of some very good recordings that we made last year, and so we'll have as a guest lecturer Professor vandenberg, who took some lectures last year. So you'll even get a 4th perspective.
Bonus lecturer.
So it sounds like an infomercial. Yeah, it sounds like an infomercial. Buy 3 for the price of 1. But wait, there's more. Subscribe now, and you'll get Professor vandenberg's lectures for free.
There we go.
Yeah.
There have to be some advantages to the way we are doing things now.
Yeah, but some of you will know Professor vandenberg already. He's teaching discrete structures this semester, which some of you are taking as well. Our math students, our computer science students. So some of you will know him already. So he's not a complete stranger to the group.
Indeed. Well, I think we've all been keeping very busy with this module, and I think that's good. It's good to be engaged and to play around with these ideas. We have to play around with them all the time. That's the way we grow our brain and learn the new ways of thinking. But I must say, I am very much looking forward to the nice, long Easter weekend coming up. It's going to be a valuable chance to catch our breath.
Yes, I'm going to take a nice long nap.
I'm looking forward to Easter eggs.
There we go. Well, let's keep on going full steam ahead. Until then, see you online. Cheers.
Bye.